Alright, so functional group chemistry deals with the types of reactions that take place in organic chemistry, focusing on different classes of compounds and what takes place at the site of reactivity, so at the functional groups. So in order to understand functional groups, it's important to first get a grasp of the different types of reactions that we will come across and some key definitions. So the first type of reaction that we are going to define is our substitution reactions. So as the name suggests, substitution reactions are reactions in which a substitution takes place, or in other words, a swap is going to take place. So for example, if we have this compound here, if we have this methane here, we know that because the carbon here is only involved in single bonds between carbon and hydrogen, it's not going to be very reactive. It's not going to be able to have anything added to it because this is already saturated. So if we want to change how this molecule looks, we can't necessarily add anything because it's saturated, but what we can do is swap what we already have for something else. So for example, we can swap this hydrogen for bromine, and then that would be a substitution reaction. So once again, in substitution reactions, a swap takes place. Now, when we talk about substitution reactions, we can further break this down into two main types. So our two types of substitution reactions are nucleophilic, and we also have our electrophilic. So a nucleophilic substitution reaction, as the name suggests, will be a substitution reaction in which something is swapped by a nucleophile. And so we have to define what a nucleophile is. If we break down the name, we can see that there's this phile here, which means loving, and this nucleo here, which means nucleus. So we're talking about something that loves a nucleus or is looking for a nucleus. So the species itself, a nucleophile, is going to be electron rich. And because it has spare electrons on it, it's going to be seeking a nucleus to fill up that space. So for example, if we look at a hydroxide ion, which is this, OH minus, and if we draw that out, we know that oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. We know that hydrogen has 1 valence electron. And then because of this minus here, we need to add another electron. So we'll draw that in here. And this is how we would indicate that this is an ion. So that's our hydroxide ion. So if we have a look here, this pair of electrons is involved in a bond between hydrogen and oxygen. But then this one here, and this pair here, yes, they are part of the oxygen atom, but they are not involved in a bond. And so we call these electrons lone pairs. And any species that has one or more lone pairs would be a nucleophile because it's looking for something to fill up this space, and this space. And so it is seeking a nucleus, hence the term nucleophile. So as a definition, we can just briefly write that it is nucleus seeking. And what we've done is we've just broken down what that means. So because of these lone pairs of electrons, it's looking for something to fill up these spaces, hence the nucleus seeking definition or term given to this species. So in a nucleophilic substitution reaction, we're going to have a swap take place, but that swap is going to be something being swapped by a nucleophile. So for example, if we take methane once again, this is what methane looks like. In a nucleophilic substitution reaction, we might swap this H for an OH, because we know that OH is a nucleophile, and so that would be a nucleophilic substitution reaction. The next type of substitution reaction is our electrophilic substitution reaction. And so we can probably already guess that this is going to be a substitution reaction in which something is replaced by an electrophile. And an electrophile is something that loves electrons. And so the species itself, or the electrophile, is going to be electron deficient. And so that could be anything from a cation, so a positively charged ion, or an atom involved in a polar bond in which that atom has less pull on shared electrons. So for example, if we have a look at this bond here, this is a bond between carbon and fluorine. And we know that fluorine is electronegative, and so it has a greater pull on shared electrons. And so because of that, fluorine is going to have a slight negative charge because it has a stronger pull on these shared electrons, whereas carbon is going to have a slight positive charge because it has a weaker pull on the shared electrons. And so carbon in a carbon-fluorine bond is going to be an electrophile. So electrophiles are not just cations. Yes, cations are an example of electrophiles, but also atoms with less pull on shared electrons are also electrophilic. So that covers our two types of substitution reactions. We've got our nucleophilic substitution reactions, and we've got our electrophilic substitution reactions. And so essentially we can summarize our electrophiles as anything with a positive or a slight positive charge. So the next type of reaction that we're going to look at are our addition reactions. And so we've already touched on this, but substitution reactions are different from addition reactions because rather than a swap taking place, something is added on to the compound. And so an example of this is if we take a look at this compound here. So we know this is ethene, and because there is a double bond here, so this is unsaturated, what can happen is we can break one of these double bonds, and because of that, we can now add another hydrogen on here and another hydrogen on here, because we've broken a bond and therefore we've been able to add another bond in order to satisfy the rule that carbon needs to have 4 bonds. And so that is an addition reaction. The next type of reaction that we're going to have a look at are our combustion reactions. And combustion reactions are simply our reactions of burning. So colloquially, we refer to them as burning reactions, but more critically, combustion reactions involve the addition of oxygen. Our combustion reactions are a type of oxidation reaction. Now, when we look at combustion reactions, we can look at complete and incomplete combustion, especially when we talk about the combustion of hydrocarbons. In all combustion reactions, H2O is produced. And remember, this is in all combustion reactions. In complete combustion reactions, we're also going to have carbon dioxide produced. Where we have limited oxygen available, we're going to have carbon monoxide produced. And if we have no oxygen available, we're going to have just carbon produced. And so that makes sense. If we have a look where we have complete oxygen, where we have a lot of oxygen available, so excess oxygen, we're going to have carbon dioxide produced. Where we have limited oxygen, rather than having a dioxide, we're going to have a monoxide, so carbon monoxide. And where we have no oxygen available, well, we can't put any oxygen onto our carbon, and so therefore we're just going to have carbon produced. So those are the three types of reactions that we're going to come across as we study our functional group chemistry. So just to recap, we've got our substitution reactions, and under our substitution reactions we've got nucleophilic and electrophilic substitution. We've got our addition reactions, in which a double or triple bond is broken so that something can be added on to a compound. And then we have our combustion reactions, or our burning reactions, in which we have an addition of oxygen. Now, if we have excess oxygen in the atmosphere where the combustion reaction takes place, we're going to have water and carbon dioxide produced. If we have limited oxygen in the atmosphere where we're going to do our combustion reaction, we're going to have water and carbon monoxide produced. And if we have no oxygen available as we do this combustion reaction, we're going to have water and just carbon produced.